Hey guys, it is Dr. Mandis here, coming in today to talk to you about IMF, not the International Monetary Fund for you econ majors, IMF's intermolecular forces of attraction. These are the attractions that hold particles together in substances. It's kind of like a bond, but bonds are within the molecules, holding the molecules together. We're talking about the attraction between the molecules. What holds like your sheet of paper together? It's not one big giant molecule, but something has to be holding the particles together, otherwise it would fall apart. Okay. There are about, I don't know, about half a dozen or so different IMFs I want to talk about. We're going to go from harder to easier, and we're going to start with the covalent ones because IMFs are linked to the types of bonding that are within the molecule because the properties of the molecule itself, you know, they determine how the molecules are going to behave, how they're going to interact with each other. So first off, we have things that are found in polar covalent bonds. Polar covalent bonds are found in polar molecules. But anyway, the first is dipole-dipole. Alrighty, what we have is a polar covalent molecule. In a polar covalent bond, you have a very electronegative atom sucking electron density over to it. So like in the CO, your electronegative atom is right there, the O, not so much the S. The S and the C have really similar electronegativities, not different enough to create polarity. And that's the subject of another video. So anyway, the electrons are way down here on the O. So what you have here is a region that's becoming slightly negative, okay, and a region that's becoming slightly positive. They're like, partial negative, partial positives. They're not full-blown charges because I don't want to be covalent, be ionic. But anyway, the electrons in this dipole, two poles, two regions of charge, the electrons are moving down towards the O. We call that a dipole moment. I don't know why it's not a dipole movement, but it's a moment. But anyway, I digress. So what we have there is one dipole moment going to the O. Over here we have another dipole moment going to that O. And what happens is those two substances are going to line up on each other because the one negative and the other positive, this negative, well, one end is going to be attracted to the other end. And if you think of a whole mess of these things, then throughout the entire substance, they sort of line up to each other because opposite things attract. And that's a dipole-dipole interaction. It's a fairly, as they go, it's not the strongest interaction, but it's a decent sized interaction. A really specific dipole-dipole that's stronger than a normal one, that's why it gets a special name, is hydrogen bonding. Hydrogen bonding is really specific. A mnemonic that I like to use is hydrogen bonding. Hydrogen bonding puts in the F over N because what a hydrogen bond is a hydrogen that has to be attached to an F over N is attracted to the lone pair electrons on another F over N. It only works in that second energy level of F over N, highly electronegative atoms with valence electrons in the second energy level. So only F over N. So think hydrogen bonding and you'll remember it. Anyway, I've set up two water molecules here. We have dipoles from the H to the O. The O is more electronegative, just like it was up here. The electrons are going to move from the H to the O. The other dipole, the electrons are going to move from the H to the O. And what we have here is a special dipole-dipole interaction between one end of the bond and the other end of that dipole, I should say. And it's just hydrogen bonding. It's a little bit stronger of an interaction, which is why it gets its own special nomenclature. Next, we have a weaker sort of induced dipole. The dipole doesn't really exist. It's just an induced dipole and what we call a London dispersion force. In some biology classes and other classes, you might hear them as van der Waals interactions. What happens is the electrons in the atom are inducing dipoles in the atom right next to it. I have a sketch of it down here, but I think it'll be better if I draw it. All right, if you have one atom, basically, I want my drawings to be as nice. The electrons in an atom can be anywhere in the atom. That's just the way it is. Electrons are always wherever they are. There's quantum particles, so they're part of quantum theory. They can be anywhere in the universe until they identify where they are. So there's a chance that the electrons could all be, or a lot of them could be on one side. If they're all on one side, that's what the green's showing you. If they're all on one side, then you can sort of get into the nucleus. So what's happening there is one side of the atom is becoming kind of negative, and the other side is becoming positive because the nucleus is being exposed. Now, that shift in electron density to one region of the electron cloud will cause the next atom over to shift its electron density because those electrons are going to be attracted to that cute little nucleus there. And so again, you're going to do another dipole. So I'm trying to show you down here with how the dipoles are kind of lining up with each other. A positive with a negative, positive with negative, positive with a negative. They're very weak interactions, as you would suspect. The odds of all the electrons are moving over for a long period of time, not that good. But they are in constant motion. They can be over there. These are real effects. London dispersion forces are in everything, but they're very weak interactions. I liken it to money. If you have a nickel in your pocket and it's all you got, it matters. But if you got a $20 bill and a nickel in your pocket, you don't really worry about the nickel, unless, of course, it's $20.04 at the register, then you're happy to have that nickel. So London dispersion forces can play a role, but they're not usually the primary role. But sometimes, especially if it's nonpolar covalent substances, it's the only IMF you're going to get. And later on in another video, we'll talk about that and show about how the halogens go from melting at minus 220 degrees C to 114 degrees C, all because of London dispersion forces increasing because iodine has a lot more electrons than fluorine, and so it can induce a much stronger dipole. Moving onwards out of covalent bonding, we go to ionic bonding. The ionic IMF is pretty obvious if you know what ionic bonding is. Ionic bonding is a cation surrounded by anions, and those anions surrounded by cations. Okay, the ionic bond and the ionic IMF are pretty much the same thing here. In covalent bonding, the covalent bond is within the molecule. The IMF, the dipole-dipole, the hydrogen bonding, the London dispersion, those forces are between the molecules. Okay, ionic IMFs, there are no molecules. They're just cations and anions. The ionic IMF is the force that's holding it all together. It is the exact same as the bond. It's a bit of a nomenclature. But the thing you got to realize is that, hey, a bigger cation with an anion is going to have a stronger IMF than a less positive charge with that same anion. They're still subject to Coulomb's laws of attraction. Smaller distance between the particles increases the strength, and the larger the charge increases the strength. Ionic IMF is a very strong IMF. That's why ionic compounds, salts, tend to melt at really high temperatures, unlike covalent compounds, where those IMFs tend to be weaker. Ionic is one of the predominant IMFs. Ionic IMFs are strong, but so are metallic IMFs. Metallic IMFs are within just metal substances. I talked about this in a previous post about bond types, how if a metal atom is basically with other metal atoms, their valence electrons are very loosey-goosey. The valence electrons are moving throughout all of the atoms. It's what we call delocalization of those electrons. And that delocalization of the electrons ties all the metal atoms together. Metallic forces can be very strong. Some metals can melt in the palm of your hands, but most metals have really high melting points because that metallic IMF, that metallic bond holding the metals atoms together in a substance, is a very strong interaction. It is only found within metals. Less common IMF that's also wickedly strong is a network covalent. Typically, they're very rare. In my class, I ask people to memorize just 3 of them. Sand, your silicates, in this case we'll just simplify silicates as SiO2, and 2 forms of carbon, diamond and graphite. Network covalents are just that, networks of covalent bonds. A covalent bond is a strong gig, but usually only within the molecule. To melt something, to mess with the IMF, you're messing with interactions between the molecules, not within. Like when you boil water, you don't change water, you just change the IMF, you undo the IMF. Well, sand is a good example of this network thing. You can picture it in 2 dimensions anyway, that an Si atom bonds to 2 O's. Well, it forms 4 bonds to 2 other O's, which go to another Si, which go to another bunch of O's. And this can just go on and on. The net result is that for every Si, you have 2 O's. And basically because it's a set network of network covalent bonds or strong bonds. Diamond and graphite are the same gig, but just between carbons. Diamond tends to be stronger than graphite because graphite tends to be stacked like dinner plates. The IMF is spread within the layer, not between the layers. What a diamond does is it connects the layers. So that diamond is strong through all 3 dimensions. Those are IMFs. They're just the glue that holds the particles together in a substance. In another post, we'll talk about how IMFs relate to boiling points and melting points. But for right now, you just recognize the IMF based upon the bond type. Hope this helps. Have a good day.